All right, so welcome to this small little tutorial of how I would go about browsing through the PintOS source code. So I'm creating this tutorial just because I figured that many students are still trying to understand how to read the source code and how to go about modifying PintOS. Hope this tutorial helps. All right, so hope you have the VirtualBox installation, the OVA file installed properly on VirtualBox, and your basic interface would look something like this after you log on. Okay. So what I do initially is I enable the workspaces. So because I have 4 different workspaces here, I can maybe browse through the source code in this particular desktop, and then I can search for some other thing here. I can do the make check here, and then I can see the source code of the test here. So this is how I organize my desktop. All right, let's go to this first desktop. Now, what we do here is we open up a terminal. So I make this thing full screen. I increase the font size a little bit. I go to PintOS directory, PIN, just hit tab and it auto completes for you. I hit the enter key, and then under PintOS I go into SRC folder. Inside SRC folder I go inside threads. So I hit Ctrl L, which will clear the screen for me. Then I type in ls, which shows me all the files that are currently existing in the system. Okay, so I have one window that is set up. So let's go to another desktop here. I just come down, that is I hit Ctrl and Alt and press the down button, so it comes to the second window. So I open up a new terminal in this workspace, and here I go into the PintOS directory. I can either put in $PintOS or I can just type in PintOS itself. So PintOS src threads, right? Then inside threads, the place where I would go about creating and making the build files is in the build directory. Okay, so I already had done some make tests before, so because of that you can see kernel.o already here. So when I type in make clean, all these things go away, so you can just see like the basic folders which are there. Your .object files have gone. Alright, let's clear the display and let's go to the first workspace. Now let's just open up another terminal on the right sided workspace, just in case we want to search for something. So I open up a new terminal here. I increase the font size a little bit. I go to PintOS and SRC, and in SRC I go under threads. Great. So we have all our 3 workspaces set up properly. Okay. So the text editor that I use the most is called Vim. So Vim is really efficient in case you're doing programming from the command line. So let's see thread.c using Vim. So I open up thread.c, and remember all this autocomplete works because I'm hitting tab quite often. And you can see a file that looks like this. Okay, I have enabled numbering here. The way in which you would enable numbering is by hitting shift : okay, you can see the cursor come down here. I just type in set nu. So when you type in that command, you can see the numbers come up on the left hand side, and having those numbers is helpful in case if you're debugging later on. Okay, so I have my thread.c file that's open, and it has got 500 So as I was saying, yes, we are right now exploring the threads thread.c file. So inside thread.c we see many functions here like thread init, thread start, and other thread functions. So if in case if you're trying to look for maybe thread block definition, you just hit /thread underscore block and you can see the definition of thread block here. Okay, now I just want to see when I'm in Vim, I just want to see some other file that is also present alongside, just in case if I want to see if there's a function call happening between files. So what I do in Vim is I open up a split window. How I do that is hitting Ctrl W and V. So when you do that, it just creates a different it just creates a split screen but with the same file itself. But for example, if I want to open up a different file, in the command mode I enter, command mode is whatever you put in your colon here. So I put like E stands for explore, current working directory. So I scroll to a device folder, for example. In the devices folder, I want to see how does timer work. So I go to timer.c. So inside timer.c, if I want to see, like, you know, just the timer ticks, how timer ticks is implemented, I would scroll down here. Okay, and the way in which I scroll is by using J and K. J is for going down and K is for going up. All right. So what you can see here is your busy wait loops. You can see like the real-time things, and anyway, this is all like how your timer is implemented. You would have to go about changing specific pieces of code in this particular file. More specifically, your this particular function here. Hold on, I'll just bring it up. Yeah, there you go. Your timer sleep. Right now, what it does is it sleeps, and the way in which it sleeps is by calling thread yield. Now, if I want to see the definition of thread yield, I go back to this previous file in thread.c. I type in thread yield here. Okay. Now, thread yield, the implementation is shown here. So all you can see is some comments of how thread yield works. Yeah, anyway, and what you would end up doing is maybe just add some few comments here. Okay, I would add something like printf. All right, printf. In thread yield, something like that. Okay, but yeah, you can go about doing any things like this here. Write your own function call here and then create your function somewhere above this. You can do whatever you want. So basically, as part of your first assignment, which I will be sharing with you in a few days time, you would have to re-implement this. The way in which you would re-implement this is by eliminating the busy loop which is happening here, and then by invoking proper calls to certain functions that do not busy wait. Okay. All right. So let's try compiling this project. So let's go to the workspace on the right. So here, let's go into the build directory. In the build directory, let's go to yeah, let's do make here, or just to be consistent, make clean. Okay, and then we type in make again. So right now it's making. It'll compile the project. Okay. So only when you get output. So only when you get an output like this, without any errors here, it means that your project is compiled. Or else if you see some errors here, it means that there are some errors and you have to recompile your code, because whatever grading you're trying to do after compiling with errors, your grading is not going to be affected at all because the project didn't compile at all. Okay. Anyway, so inside build, okay, we find that new .object files have been created. Now we want to see how much grade would you obtain if I give out your project 1. So initially your grade would look like this. The way in which you would check your grade is by typing make grade. Okay. When you type in make check, it checks all the tests which are present, but make grade computes the grade for you. And this would take some time to complete, so let's wait. So for every single test, what you notice here is you would notice the difference between what is expected and what is currently outputted. These multi-level feedback queues execution usually take a longer time. I've given 4 GB memory for this VirtualBox image, and I think it's sufficient enough for the way in which I am going about developing in VirtualBox. I don't notice any significant lag here, but you can give in definitely more memory and see if it suits your needs, but just 4 GB is sufficient for my needs. All right, we are almost finishing. Okay, there you go. So your make grade has computed, and the way in which you would check your grade is by going to there's already a grades file which has been opened up here, so which has been created here. So I open this grade file and I see the summary of my test set. So by default your points would look like this: 14, 0 and 8. So by the end of project 1, your total, your maximum would be the sum of all these 3. Okay, when you implement your priority scheduling properly, you would get a maximum of 38 points. Similarly for MLF queues. Okay, so when you see the summary of individual tests, it shows you how many tests have passed and what have not passed. These 2 stars means that you're getting absolutely 0 and the functionality has not been implemented at all, or in case if it's implemented, it's not working properly. Okay, so there you go. Like, all the information you require is present in this grade file. All right, so I've shown you how to check your grades by yourself, and in case if you want to run a particular test, you would do this. You would say PintOS. So just because I know that there's an test called alarm single, I would run this, and I would given this flag PintOS -q just to make sure the box screen exits after running this test. Okay, so there you go. The box came in and it disappeared, right? So basically whatever output I see in that box is what I see here. Alright, so that's how you run a single test, and in case if you want to see the output of that single test, you would go into your tests folder that's under your build, remember, and go into threads. Yes, so as I was saying, I checked for alarm single, right? So all these tests have actually run. So let's see the result of alarm singles. So I use cat. Cat is just basically your command line output uh, output program. So what it does is I just put in cat alarm and single dot result. So as you can see, the single dot results, by default it is passing. Let's see another test. Single and now negative. Okay, so it's also passed. Now in case if I want to see the some other error like alarm multiple error, so I put in cat alarm multiple errors. Okay, so there's no any major error, so it just shows like the box simulator startup. Alright, now in case if I want to see the result, if I want to see the output of alarm 0, then I can do something like this, alarm 0 dot output. So there you go. You can either use cat or you can use vim to open up whatever files you have. But when I open vim just to see some content, I need to close it. So that would involve a lot of keystrokes. So because of that, I use cat. Okay. So anyway, I've shown you how to browse, and I've also shown you how to run your grading scripts and also how to check individual tests. All right. Now sometimes you might want to check very specific details. For example, you would want to see where is your external function, external hardware devices definitions existing. So the tool I would use to search for the entire source code is called grep. So it will match every single instance a word occurs for the entire source code. So let's see, inside threads, this thread source code, I want to search for external. Okay, so this is how I would go about typing the grep command. So grep minus nr, the word that you're searching for external, and in the current directory. So there you go. You get like all occurrences of the word external. So you see in interrupt.c at line number 43, this is where external is used, like in one of the places, and also at line 47 it's used as part of a variable name, and so on and so forth. In case if I want to actually check the validity of this, I open up interrupt.c and let's see for line number 355. I go to line number 355 in vim, and there you see external is defined here, and you can read comments about how they are used, and PintOS is very well documented. So I've shown you about grep, I've shown you about vim. Now the last thing which I would like to show you in this tutorial is how to use GDB. Okay, so I clear this screen by using Ctrl L, and I open up another terminal here. Okay, I open up a new terminal. Alright, now I just place it here, and I always I want to make it always on top. Alright, I increase the font size, reduce the size of this. Alright, great. Now I go into the build directory under threads. So I would run PintOS GDB. There you go, I got the command. This is the command you need to run, PintOS GDB run alarm single. This is run and you can pass in whatever test. Alright, so this is the command I type in here. So run alarm single is the name. Alarm single is the name of the test. So I type in enter here. Your box screen is created. Okay. Now, in another window which I always put on top, I type in PintOS GDB, and I get this GDB connection here. Okay. So what is happening is this particular screen in the background is waiting for a GDB connection, and in this screen we are creating a GDB connection. So what GDB stands for is GNU Debugger. So it's basically used to check whether your code works properly by listing all your thread elements, by listing all your stack pointers, by listing the values of all the structures you have. That's very useful in case you end up getting stuck, or your kernel just halts and it's just your code is really messy and you want to know how the control flow of information looks like. Okay, so anyway, in GDB there's a macro called Debug PintOS. I entered that, and there you go. A connection was actually made to the background process, and GDB has said like some remote failure has replied with some codes, some are errors and all these things. Never mind. But as you know that with reading through these messages says that there's a reply that has been sent by the remote. Okay. Now what I do is C is for continuing the execution. Okay. So as you can see, it's continued until the end. So you haven't set any breakpoints here, so your single alarm just finished its execution, right? So usually you wouldn't want that to happen. You would want to set breakpoints somewhere just to see where your code is throwing up errors. Okay, so let's rerun this again. So let's quit this instance of GDB. Okay, and let's rerun this alarm single. Okay, now this process is waiting for a connection. So let's start PintOS GDB, and here in GDB let's go and to debug PintOS macros. Here what I do is I set a breakpoint at a function called schedule. Okay. I continue first here. I hit Control C and I set a breakpoint at schedule. No. What happened? Okay, let's try it again. Yeah, so sorry about the error in the previous recording. It just seems that when I was running PintOS here, when I invoked PintOS GDB, I should invoke kernel.o along with that. So let's go into PintOS, and in PintOS src, inside the src folder the threads, inside the threads the build, and inside the build your kernel.o, right? That's how your PintOS GDB knows your kernel.o file exists. Okay, that's how it knows that through the kernel.o file you can extract the symbol table, right? So there you go. Your symbol tables are loaded from this object file. So here, there you see here the error does not happen here just because your kernel.o file is loaded correctly and your symbols are all correctly loaded. Okay, so there's no end of file error, whatever, as we saw before. So let's set a breakpoint here on schedule. Okay, so schedule is a function which is located here in your thread.c, right? So let's see, where's your schedule defined. I saw some schedule here. Let's go star. Yeah, see, this is this. As soon as the execution comes to this point, it means that your debugger would stop here. Okay. So let's go to the debugger and then click on the continue. The program is not being run. So I set the breakpoint here, and then yeah, I go to Debug PintOS because this GDB connection is waiting for this this one here. So anyway, well, we see the error back here again, as I was saying before. Well, never mind about this error. Now what we do now is we just hit continue, okay, and we see that the breakpoint 1 has been reached at line number 554. Now in line number 554, we hit next, and then it goes to the next one. If you just hit enter, it's by default, it means whatever the previous instruction has been put has been entered. So I just hit enter here. It just says, it just takes in the inputted command of n. Okay, then I put n, n. So as you can see that all the function calls that have been used here are being displayed. So you can then see like where the jump happens. So you go more and more, just hit this thing more and more. You would see like schedule, once again breakpoint has been reached. I just keep on entering, and you can see like what happens is your GDB says that your switch thread is called after a period of time. So in switch thread your inside switch thread, your switch.s is invoked, which is just basically your assembly level instructions. Okay, and you just keep entering. You can see many functions called, and you can see the flow of execution of this program. All right. So hope this small little tutorial is helpful to you, and good luck with your project 1. I would post many tutorials like this online in the future. So this is the first time I'm doing all this tutorial composition. So in case if you find the video to be slightly misaligned here and there, I'll make sure that next time I'll be pretty careful. All right. Okay. Thanks for watching.